Hello, my name is Lei Jun Lam, and I will discuss the front part of the task 1. So let's look at the question. A campus print shops require a closed cylindrical mailing tube with a fixed internal volume of 0.01 m3, which is equals to 10,000 cm3. Now, using the concept from engineering math, we apply a single variable calculus to design with the minimum material cost. Now the curved sidewall costs Rm18 per square meter, while the end cap costs Rm28 per square meter. Our objective, of course, is to write out the CR with only the variable radius R. So when we look at the next slide, the area for side wall is 2 pi r h, which we have the h unknown variable. Now we look at the area for end caps is 2 pi r squared. Now we all know about the volume for cylinder is V equals to pi r squared h. Now when we only want to have one single variable inside our CR function, we try to kick out the h unknown variable. So what we can do is we express the h in terms of the r using volume. So we will get h equals to V over pi r squared. Now we write the cost function. The CR function can be write as the cost for side walls multiplied the area for side walls plus the cost for the end caps multiplied by the area of the end caps. Now we bring in the value that we write just now. So we have CS multiplied by 2 pi r h plus CE times 2 pi r squared. Now because of the h there, we couldn't do any differentiation, so we substitute h into the equation. Now h equals to V over pi r squared. Now we substitute it inside, we can get 2 pi r bracket V over pi r squared CS plus 2 pi r squared CE. Now here we can simplify the equation, so we get 2V over RCS plus 2 pi r squared CE.
So I will continue the next part, which is I need to find the equation of the derivative equation of C to respect of R. So here we just need to do it with the way dr times by 0.36 per r plus ddr 56 pi r squared. Then this one becomes 0.36 r to the power of minus 1. We move down the minus 1 into here, and then we just need to subtract the power by 1, and for this one we move the 2 down here times by 56, and then for the power we just need to subtract it by 1. So it becomes, the new equation becomes minus 0.36 r to the power of minus 2 plus 112 pi r. After that we just need to find the stationary point, which is the equation equals to 0. So we just need to substitute it to 0, and we move this one into the right side, so both sides become positive. After that we just need to times both sides by r to the power of 2, so this one dr is gone, and this one become r cubed. After that we move this one into down here, so it 0.36 divided by 112 pi. Then we just need to calculate it, it becomes this one, and then we just need to cube root it, so it becomes r equals to 1.00764. After that we just need to find the h. We substitute the r by this value, and then we just need to calculate it, so we find the height, it equals to 0.3135 meter. After that we need to find the value of CR2, the cost, and then we just need to substitute this r by 0.11764, and then we do the simple calculation, and it becomes 5.359 ringgit for the CR cost. After that, we got the new case when NCAP's cost rise to 35 ringgit per meter squared. We need to find the new R here. So first we need to time this 35 times by 2 because there is the bottom part and the top part. After that, we just need to derive this equation. It's the same. Minus 1 here becomes minus 0.36, and then it becomes the power of minus 2, and then here 140 pi r. After that, the same way, we just need to equals the equation to 0. Then here we move both sides, so become positive, and then here times by square, r square, so this one gone and this one become r cube. After that, we just need to divide it, and we need to do the cube root. So we find the r equals to 0.094 meter. So the conclusion is when the NCAP cost rise to 35 ringgit per meter square, the r decreases. This happens because the NCAP cost depends on the r. So by making the CE more expensive, the r will become smaller, making the tube narrower. That's all from me. Thank you. Okay, now we need to find the second derivative test, which is the verification of minimum cost. So here we got the first derivative equation already. Then we just need to derive it again. So here the minus 2 becomes minus 3 for the power, and then here minus 2 got moved down. Minus 2 times by minus 0.36 becomes 0.72, and then here the r here gone because it got subtracted by 1 2, so it's become r to the power of 0, which is just 1. And then we got the positive equation here. Since r is bigger than 0, so of course automatically this equation is also is bigger than 0. So this shows that the stationary point r is a minimum, which is this is the cheapest cost.
My name is Natalie Samantha with the student ID CME2509103, and now we're going to move on to task 2, which takes into account of a billboard mentioned in task 1. And we're going to be calculating the center pressure of this billboard. Now, we are given B equals to 5 meters, H, which is the height measured from the bottom edge of the billboard, equals to 4 meters, P0, which is the pressure recorded at Y equals 0, equals to 4 Newton over meter squared, K equals to 12 Newton over meter cubed. Now, we can calculate the height-dependent wind pressure using Py equals to P0 plus K times Y, with the condition that Y is more than and equal to 0 and less than and equal to the given height, which will be 4 meters. We can also calculate force using force, or F, equals to the integral of Py times B evaluated from 0 to height. The first step of our calculation will be finding the center of pressure from the bottom edge of the billboard. We can plug in all of the given numbers into the height-dependent wind pressure equation. Now we have Py equals to 40 Newton over meter squared plus 12Y Newton over meter cubed. Now, we can see that based off of these values, we can tell that Y's unit is in meters, and Py's unit will be in Newton over meter squared. So we can plug it all in and we can get Py equals to 40 plus 12Y, which we can take this function and immediately input it into the force equation, which will give us F equals to the integral of 40 plus 12y times 5 evaluated from 0 to 4, which will give us 200 plus 60y. And over here we can find the integral as 200y plus 60y squared divided by 2, which will give us 200y plus 30y squared. And this is how we get this value. Evaluated from 0 to 4, we get 200 times 4 plus 30 times 4 squared minus 200 times 0 plus 30 times 0 squared, which will equal to 0. And we can get the final value of force equals to 1,280 Newton. Now we can now input our Py value into the YCP equation given to us, which accounts for the center pressure of the billboard that we're trying to find. So YCP equals to the integral of y times Py times B evaluated from 0 to the given height over the integral of Py times B evaluated from 0 to the given height. Now, if we can see from the denominator, it is exactly our force equation, so we can immediately substitute our force value into the denominator. So we have YCP equals to the integral of y times 40 plus 12y times 5 evaluated from 0 to 4 over 1280 Newton. Calculating the numerator will give us 200y plus 60y squared. Now we can treat this denominator as a coefficient, and so we will have 1 over 1280 times the integral of 200y plus 60y squared evaluated from 0 to 4. Now this process will give us 200y squared divided by 2 plus 60y cubed divided by 3, which will result in this value, 100y squared plus 20y cubed. We can separate this and calculate it by itself. 100 times 4 squared plus 20 times 4 cubed minus 100 times 0 squared plus 20 times 0 cubed, which will ultimately give us 0. We will ultimately get 2,880. Now we can input it back into our YCP equation and divide it by 1,280, which will ultimately give us 2.25 meters. Therefore, the billboard's center of pressure is at 2.25 meters from the bottom edge of the billboard. The next step is to find the center of pressure when Py equals to P0. So that means our Py value will be equaling to 40 Newton over meter squared. Now we can input P0 value in the place of Py in our YCP equation from earlier. Now we'll get YCP equals to the integral of y times 40 times 5 evaluated from 0 to 4 over the integral of 40 times 5 evaluated from 0 to 4. Now 200y divided by 200, which we can simplify as y over 1. Integrating that will ultimately give us y squared divided by 2 divided by y. Simplify this into y squared divided by 2y, and so we will ultimately get 2 meters. Now, the height-dependent wind pressure increases with height, and when the pressure is uniform, YCP is lower. The pressure is spread evenly on every point of the billboard surface, therefore the resultant is right on the center of the billboard, which is half the height. In a non-uniform case where P0 is less than or over than Py, the height will increase and decrease linearly with the amount of pressure.
Hi, my name is Jessie and this is Hashri, and he's asking for when optimization the design of the cylindrical milling tube in task 1. You are trying to minimize of the error for each optimization cycle. After each cycle of optimization, the design error is 60% of the previous error. For instance, the initial relative error is equal to 5%. After n cycle, this is the equation, and find the smaller integer so that the design error is smaller than 0.50%. So it already given that E naught is equal to 5%, so we sub into the equation, so we will get ln 0.60 power of n smaller than ln 0.10, so we get the n equals to 4.5 in the end, so we round off to 5. So to further improve the design, you introduce a boosting algorithm that reduces the error 70% in the first 2 cycles and by 60% in each subsequent cycle. Compute the new minimum m to be 0.5% error. The first 2 cycles is 70% reduction, so we need to times 0.3. From cycle 3 onward is 60% reduction, so we need to times 0.6. So we sub into the equation, then evaluate the error after the 2 cycles is equal to 0.45%. Since 0.45% is smaller than 0.50%, so the design error requirement is already satisfied at n is equal to 2. Therefore, n only can equals to 2. So each cycle takes 20 minutes initially but becomes 10% quicker per cycle thereafter. If you stop at the n cycle found in the first part without boosting, compute the total times and its numerical value. So for part C, the first optimization takes 20 minutes and each subsequent cycle is 10% faster. Since 5 cycles are required without boosting, the total optimization time is calculated to be 81.9 minutes. So In conclusion, the boosting algorithm significantly reduced the number of optimization cycles and improved the overall efficiency of the design process. So that's all from me. Thank you.